So we're continuing on. You know, I do post videos of the lectures on YouTube. If you missed something, you want to go back to see it. Although I forgot to start the recording on this one. But we're just continuing on with chemical reactions. But you know, this is a very famous reaction. You know what this is called? Aqua regia. A mixture of HCl and HNO3 is aqua regia. You know what's special about this reaction? I'm sorry? It's used for, well, it's kind of like gold plating, yeah. What this is, aqua regia is used for is to dissolve gold. Aqua regia, you know, it's very hard to dissolve gold. If you tried like HCl, it doesn't work. If you try HNO3, it doesn't work. But if you have a combination of HCl and HNO3, it works. Why? What type of reaction is that? Well, you could say that's the aqua regia reaction and just memorize reaction by reaction. You know, a lot of people do that. But actually, this is when I look at this reaction, it's a combination. You know, this is a combination of a redox and acid-base reaction. Sometimes it's confusing because both of these are combination reactions, but they're totally different. The first one is a redox. Redox being oxidation reduction. The second one is what we call an acid-base combination. But in the earlier classification, even in Petrucci, he called both of these combination reactions. But they're totally different. And so what Petrucci does is he looks at the form, and A plus B yields C. You know, we can't always do that, A plus B yields C, because it gives us different types of things, you know, or an AD plus CD yields EF, you know, something like that, or whatever. And so we have all these forms, but what I like to do is I like to divide the reactions in terms of a common feature that they all share. And so if we could do combination reactions, they all share this common feature, then we could call combination reactions a category, but it doesn't quite work that way. And so the categories that we're going to break these down into are just three categories. These are the three categories of reaction we're going to look at. Metathesis. Metathesis is a fancy name for like a double replacement type reaction. Double replacement type reactions, just, you know, ions that like each other react. So metathesis, and we have acid-base and redox. And so these are the three categories. And what we're going to do is we're going to classify all these reactions. For example, a combustion reaction, what type of reaction is that? Is that a metathesis, is it an acid-base, or is it a redox? Does anybody know? It's a redox reaction. You know, oxygen's an oxidizer, methane is what we call a reducer, and methane plus O2 is going to be a redox reaction. So we don't need all these subcategories. I mean, that's just a combustion reaction. What all combustion reactions have in common, you know, are their redox reactions. And what all redox reactions have in common is they have the same, what we call driving force. You know, if we want to predict if a reaction is going to happen, we got to look. Are we going from, typically in nature, what happens? We go from high energy to low energy. Right? Do we? That's, you know, nature tries to minimize energy. So, for example, will I ever have to worry about this ruler coming up and hitting me in the face, you know, spontaneously? No, but if this were hanging above me, I'd have to worry about it falling down and hitting me on the head, right? And so the same thing here, what all these have in common is we're going from less stable reactants to more stable products, typically. And the less stable reactants, what makes them unstable? Well, you know, what makes them unstable, we understand based on redox properties. And that goes for all of these. So when I said, is this a stable mixture? No, this is not a stable mixture here. Whereas this is a stable mixture here. Well, what makes this not a stable mixture? Why is this an unstable mixture? Well, it has to do with the redox properties. The redox properties, which I started reviewing yesterday, involves the first thing we look at is oxidation state in terms of redox properties. You know? And so this is why I wanted you to review chapter 3 with the oxidation states, because here, what is the oxidation state of hydrogen and the oxidation state of carbon? -4. -4, is that the maximum number of electrons carbon can gain? You know, carbon can either, we look at the octet rule, carbon can either gain 4 or lose up to 4. So it can gain up to 4 or lose up to 4. So it's right in the middle, right, according to the octet rule. And so if it gains 4, we have things like carbide or whatever else. Well, can it gain 5? For example, CH5? Does CH5 seem like reasonable? No. And so here, we start to, this is where the memorization comes in. The memorization comes in is you have to have some reference points. You know, like I said earlier, if you move to a new city, you know, and you're unfamiliar with the city, you want to learn some reference points, right? Well, the same thing. If you're unfamiliar with redox chemistry, you need to learn some reference points. And one of the reference points is this. I'll just tell you that. A -4 on carbon makes this electron rich. We call it electron rich. A +1 does not make hydrogen poor because water also has +1 on hydrogen, and it's not especially reactive. Now, what's the oxidation state on oxygen? No. 0. Oxidation state on oxygen is 0. Is that reactive? Well, 0 seems to be happy because it's neither lost electrons or gained electrons, so it seems good, right? But it turns out, no, it's not totally happy. Oxygen is 0. It'd much rather be in the -2, like in water. Is water very stable? Yes, water is very stable. So we see oxygen here is -2, hydrogen here is +1. This is stable. Water is not terribly reactive. And so these are the types of reference points we have in mind. Oxygen at 0 is reactive. Oxygen at -2 is stable. Carbon at -4 is reactive. Carbon at this is oxygen -2 here, makes carbon +4. Carbon at a +4, is CO2 highly reactive? No, I mean, there's CO2 in air. If you get too much CO2, it's poisonous because CO2 has acid-base properties. But no, it's not. And so carbon at a +4 seems okay. We see lots of examples of carbon at +4. For example, carbonate. You know, let's say you have a limestone counter or something somewhere. Limestone is calcium carbonate. You know, if we look at carbonate, is carbonate very reactive or fairly stable? Fairly stable. What's the oxidation state of carbon in carbonate? +4. And so this is the database that you build up in your head. It's not like you have to memorize everything. It's not like you memorize individual. Carbonate's not stable. CO2's not. Carbonate is stable, sorry. CO2 is stable. Methane is unstable. We don't memorize it like that. We memorize a few reference points and then we can figure out everything else. You know? So for example, if I had this, in a redox reaction, which I'm going to talk about at the end, since I have this up here, it saves time rewriting it. But in a redox reaction, electrons, you know, the oxidizer wants electrons, so the oxidizer is going to take electrons. Where is it taking from? The carbon. The carbon is going to lose 8 electrons. You see it's going to go from -4 to +4. It's 8 electrons. And the oxygens are going to gain. Now, we see the range. Actually, this is the range of oxidation states for carbon. It goes from -4 to +4, but there are other ones. Like, for example, carbon monoxide. Is carbon monoxide stable? Or, in other words, when I ask about stability, I'm talking about redox stability. We talk about stability in 3 ways. We talk about metathesis, we talk about acid-base, and we talk about redox. And so stability is only relative to the type of reaction you're looking at. And so right now we're just looking at redox. And so, no, actually CO2, when we look at that, this carbon is +2, which means that that carbon has 2 more electrons it can lose. And so that means carbon monoxide can combust. Can you burn carbon monoxide? Yeah. Can you burn soot? You know, soot is what we call amorphous carbon, not diamond or not graphite. Graphite's hard to burn, diamond's hard to burn, but soot is okay to burn. It's still hard to burn. When you get these carbon deposits on a grill, you know, they're hard to remove, carbon deposits, you know, the black deposits on grills. Some people will burn it. Let's put a flame on there and leave it overnight, burn it off. But it will burn off eventually. But these, you know, these we see, these are capable of losing some more electrons. But if we go on to something like this, you know, will acetic acid burn? Can you burn acetic acid? Do you think acetic acid's flammable or not? Acetic acid is HC2H3O2. Can you burn acetic acid? What do you think? Well, you can memorize it. Is it flammable or not? Or you can use some of these reference points to figure it out. So is acetic acid flammable? Highly flammable or not very flammable? Well, if we look at the oxidation states, we can just figure it out. I mean, that's the first thing we do. -2 plus 1 plus 1. That means this must be 0. Yeah, it should burn, acetic acid. And indeed, it does burn. You can burn it. In fact, people burn it, you know, in your body. If you eat oil and vinegar dressing, are there any calories? Or is it 0 calorie, at least the vinegar part? Is the vinegar part calorie free, or does the vinegar part have calories? The vinegar part has calories. You burn vinegar in your body. And what do you exhale after you burn the vinegar in your body? You exhale carbon dioxide. So you completely burned it in your body, although there are no flames. It's the same kind of thing, because in thermodynamics deals with state functions. Whether you burn it in your body or you burn it on the table doesn't matter, because in a state function, the only thing that matters is what? In a state function, the only thing that matters is, this is the problem with thermodynamics. The problem with thermodynamics is, in order to be successful with thermodynamics, you have to know all the definitions. You have to know when this fails, when this works. Because you can't use it. If you just blindly use that equation, like say, for example, if you use the delta U equation and you're doing it in the open lab, you can get the wrong answer. But the problem is there's no alarm that goes off. Oh, you know, warning, warning, you're using the wrong equation. You can't use this equation. You have to have it memorized in your head that, you know, this is only valid under these conditions. The only way to know that is by memorizing it. And that's the problem with thermo. The problem with thermo is nobody wants to memorize anything, you know? And so they don't know. They don't know when you use delta U. They don't know when you use delta H. They just know how to punch in the numbers. You can't do that once you get to a certain level. Once you get to a certain level, you can't do it. And this is why, you know, some people say, yeah, the cheaters will be caught eventually, because they're going to fail miserably in the higher level classes when, you know, it's very difficult to cheat. Anyway, getting back to this. Yeah, you can burn acetic acid. How about methanol? Which one do you think is more flammable, methanol or acetic acid? Methanol, for sure. We can see that easily, because if we look at the oxidation state on carbon here, it's -3. So it's quite electron rich. And so that's redox here. And then we're going to do the same thing, metathesis, you know, what types of metathesis properties, what types of acid-base properties. So whenever we get a mixture like this, if you get a mixture of methane and oxygen, we can't automatically assume the only reaction that's going to occur is a redox reaction. We have to consider the other two types of reaction. So if I have a chemical A plus B, then I analyze it. What types of metathesis reactions occur for A-B combo? What types of acid-base reactions can occur? What types of redox reactions? And then once I've done that, then I've covered all my bases. I know all the potential reactions between A and B, right? Versus this, something like this, I have no idea. Did I not memorize it? Did I memorize it? Is it one of the subcategories, or what? Was that a comprehensive list? This is why I couldn't answer the question on phosphate, because this is the way I learned it. Unfortunately, Petrucci doesn't organize it like this. And so this is why I'm going to deviate from Petrucci just for this. The reason I broke it down into these three categories, and it's not just me, because I am a kind of a synthetic chemist, so I deal with chemical reactions a lot. And I learned this, but I learned this in a higher level, much higher level class. When I was thinking, wow, this is a much higher level class, but this is much easier than what I learned in general chemistry. Why wasn't it organized like this in general chemistry? Because it is much easier if you want to learn, if you actually want to learn reactions. And the way it's divided is based on driving force, And the driving force is basically, we want the formation of more thermodynamically stable products from less stable reactions. And so we see that, in terms of the stability, we learn a little bit about the stability of those types of things there. And so in terms of descriptive, what do we look for? Well, it depends on the type of reaction. Because when we have a metathesis reaction or double replacement reaction, we don't see any oxidation state changes like this. Metathesis or double replacement reaction, actually this slide is putting the subcategories in there, but I'm not going to skip this slide. This is what the subcategories. And so all metathesis reactions are going to share a common feature. When we look at a metathesis reaction, we start to think, okay, what's unstable combination? What's a stable combination? And it's different, for acid base. What's a stable? Sometimes there's some overlap. What's a stable combination? What's an unstable? And it's different for redox. And we have three different schemes which we look at. We can put these into the subcategories here. And so for metathesis, we're looking at double replacement or ion combinations, et cetera, et cetera. For acid base, we look at Arrhenius, Bronsted, Lowry, Lewis. For redox, we're looking at single replacements, skeleton redox, redox chart method, et cetera. Those are the sub of these, but all of them are the same basic type of reaction. Well, we'll look at what constitutes the driving force in a little bit, because it's different for each type of reaction. But for right now, we have to have some basic assumptions. One of the basic assumptions is that the concentrations are going to be 1 molar, and gases are going to be at 1 atmosphere. Well, that's okay, because that 1 molar in 1 atmosphere, we know. 1 molar in 1 atmosphere is called what? 1 molar in 1 atmosphere is called standard. 1 molar in 1 atmosphere is called standard. I didn't write it down, I just said it. I'm good. That's the problem. What I try to do, in lecture, I don't write everything down on the board, but you should try to write everything down, in your notes. But it's called standard thermodynamic conditions. And so our first basic assumption is we're going to work under standard thermodynamic conditions, 1 molar in 1 atmosphere. You can go back to chapter 7, read about it. Extremely low or extremely high concentrations require compensating for. It's not that we can't work at other concentrations and other pressures. It's just if we do that, then we have to shift our thinking of what's stable and what's not stable in terms of that. And so there's some examples here. Like, for example, HCl and silver nitrate. This is a double replacement reaction, AB plus CD. Do you see that? AB plus CD yields CB plus AD. And so what we have here is we got HCl and silver nitrate going to silver chloride and nitric acid. And if you recall double replacement reactions, one of the driving forces is precipitation. Well, silver chloride is an insoluble solid, so it will precipitate. And therefore, we expect reaction to occur. The driving force would be the formation of a stable precipitate, silver chloride. But, you know, at very dilute concentrations, this doesn't happen. You know, at very dilute concentrations, you can mix HCl and silver nitrate, nothing happens. No precipitate forms. It's because the concentrations are too low. The reverse reaction should be unfavorable. Silver chloride plus nitric acid, we should get no reaction for that. But it turns out that silver chloride with hot concentrated nitric acid will produce a reaction. This is the wrong reaction. I keep forgetting to change this slide. Plus, etc. I keep changing this because, well, this turns out that it's no longer a double replacement type reaction. This converts into redox reaction, and so there's some other stuff that forms from the redox that occurs. And so this when I was taking Chem 1B, this was one thing that they did that was pretty tough at Santa Barbara City College is they had us do a project, a research kind of project. And the research project was we had to convert silver chloride into silver nitrate, solid silver chloride into solid silver nitrate. Problem is silver chloride doesn't dissolve in anything, right? Typically, you can consult the CRC, which I did. You consult the CRC says, okay, is silver chloride soluble in cold water? No. Is silver chloride soluble in hot water? No. Well, if you try hot and cold water, it doesn't work, then what do you do next? What you do next is you try other solvents. Is silver chloride soluble in alcohol? No. Is silver chloride soluble in acid? No. In base? No. And so how do you get this stuff to dissolve to get it to react to form silver nitrate? Well, that's very tough. But what I didn't know is, I knew this, double replacement reaction, but I didn't know is if you change the concentrations, other things can happen. So in hot, and temperature as well. So in hot the answer was you take silver chloride, you dissolve it in hot concentrated nitric acid, and then you can get it to dissolve. And so sometimes we get stuck in one mode of thinking because we're thinking in terms of standard thermodynamic conditions. But if we go to non-standard conditions, maybe we can get it to go. We have another reaction down here. This one, actually this is not the 2017. This is like the 2001 version. There's one more correction I'd like to make. A couple mistakes on this slide. One, put the etc. here. Two, that should have been lead-2 hydroxide, not lead-2 chloride. There are other tricky things. For example, lead-2 nitrate plus sodium hydroxide should precipitate lead-2 hydroxide plus sodium nitrate. But when you add sodium hydroxide, excess sodium hydroxide, the precipitate dissolves. Precipitate dissolves because the lead-2 hydroxide precipitate is attacked by the additional hydroxide and forms this. This one, we're going to learn how to name these this week. This is what we call a complex ion. It's Pb with 3 hydroxides. A Pb2 plus with 3 hydroxides is going to give you a net negative charge. This thing is called trihydroxoplumbate ion, and we'll learn this in chapter 24, which we're covering this week. We're just covering the nomenclature because we've got to deal with these types of species in some of these chemical reactions. The other assumption we're making is that we're looking at the thermodynamic driving force. The thermodynamic driving force is which one's more stable. So for example, diamond versus graphite, which one's more stable, diamond or graphite? You know? What's more stable, diamonds or graphite? Thermodynamically.
Right there, graphite.
Graphite is. Graphite's more stable. Graphite's more stable, so that means diamonds should decompose into graphite because diamonds are less thermodynamically stable. Graphite's more thermodynamically stable. There's a driving force, right? Nature's going to lower the energy. So do you have to worry? I mean, if your diamonds are going to decompose into graphite, it's a money-losing proposition to buy diamonds, right? But you don't have to worry because of this. We're ignoring something. Whenever we factor in whenever we're looking at a chemical reaction, we have to look at the thermodynamics and we have to look at something called the kinetics. The kinetics deals with how fast the reaction occurs. This reaction occurs so slow, we don't have to worry about diamonds decomposing at all. And so we call this kinetically stable, but thermodynamically unstable. Kinetically stable to thermodynamically unstable is given a special word. It's called metastable. Metastable. Metastable just means this. I don't have to worry. If I release the methane into this room, do you hear that? I don't have to worry about that because I know that methane and oxygen form a metastable mixture. Nothing's going to be happening. I mean, or it's so slow, right? The only time I have to worry is if I speed up the reaction by warming it up with either a flame or a hot piece of metal. If I speed up the reaction, then I'm going to see something happen. That's the kinetic. So when we're doing these types of review here for these reactions, we're ignoring the kinetics. You know, it's not. You know, usually when you have a big driving force, it turns out this is a big driving force, and things tend to happen quickly. Room temperature is not. But not always. And so we have to be aware that, you know, otherwise, if we add too many variables into this, it gets quite complicated. So we want to keep things on an even playing field. And so what we're going to look at first are metathesis reactions. Typically reactions with two or more ionic compounds. So we have more, AB plus CD plus EF plus GH plus IA. We could have a huge mixture of compounds, and we just see, you know, well, we're looking for favorable ion combinations. Well, what are favorable ion combinations? Favorable ion combinations are things that are going to precipitate, things that will form gases, and things that go from a stronger acid to a weaker acid. Stronger acids are less stable, more reactive. Weaker acids are more stable, less reactive. And so in terms of theory, we want to form more stable bonds, you know, in terms of the quantum mechanics, QM of this. And so weak electrolytes or molecular compounds might participate. It doesn't have to be ion combinations. For example, ammonia and ammonia-like compounds called the amines. Are considered metathesis type reactions. We'll look at some examples here. Well, what's going to precipitate? Well, in order to figure out what's going to precipitate, we look at the solubility rules for ionic compounds. The solubility rules, these are from Chem 4. Solubility rule 1, group 1 and ammonium. Group 1 would be sodium, potassium, lithium, etc. And ammonium compounds are all what? Are all soluble. Okay, then that's a cation. Then we look at what? And so the first thing we look at is a cation. Is a group 1. They're all soluble. 2, then we start looking at the anion. You know, if it's not one of those cations, then the easiest thing to do is check the anion. The first anion we look at is what or what? We look at the. Anyone have them memorized still, or did everyone forget them? We look at the nitrates. What's the formula for nitrate? NO3 minus acetate. C charge. We look at the nitrates, acetates, and the chlorates. What's the formula for the chlorates? ClO3 minus. Nitrates and chlorates and acetates are all soluble. These are just soluble. No matter what the cation is. So you could have lead, mercury, whatever. There are some exceptions, but those exceptions, like mercury 1 nitrate's not so soluble, but we aren't going to worry about it too much. Okay, if it's not one of those, what do we look at next? We look at the chlorides, bromides, and iodides. We look at the chlorides, bromides, and iodides, and these are soluble. Except there are more exceptions here, and these exceptions we should note. Except for what? Except for Ag+, so silver bromide, silver chloride, and silver iodide. Hg2 2+, which we call, what do we call that? Hg2 2+. Mercury 1 or mercury 2? Mercury 2? Mercury 1. This is mercury 1. Mercury 2 is soluble. So if I had mercury 2 chloride versus mercury 1 chloride, mercury 1 chloride is insoluble, mercury 2 chloride is actually soluble. It has to do with the bonding. And Pb, lead 2. Lead 4 turns out to be soluble. Those are soluble because the bonding is much more molecular rather than ionic in those species. It has to do with the quantum mechanics. Where's fluoride? Why is fluoride left out? Why is fluoride left out? Okay. Well, think about why the fluoride's left out.